And first up is Luca Fanelli. He is going to speak to the multi-technology, multi-application solutions. And he has received his MS degree in electrical engineering from the Polytech of Turin in Italy back in January of 2006. And he joined SPEA and has been part of that organization for quite a long time. And today he is the president and general manager of SPEA America. So first up, I would like to welcome Luca to the stage.
Thank you. Good morning, everyone. Really happy to be here today. So a little bit about SPEA. SPEA is an Italian company that was founded in 1976, for those of you who don't know, and we are about to close to celebrate our 50th anniversary. The last 30 years of our history, we have been involved in testing semiconductor products in general, and the last 20 in particular, testing MEMS. So we have a long history on testing MEMS, and today I'm going to address a topic that is very important for the MEMS industry because it has to deal with the standardization of the test equipment. Why that is important? Because standardizing test equipment means efficiency. Efficiency means reduced cost, which means higher margin for those who produce MEMS products. A little agenda of what I'm going to talk about today. A couple of slides showing the scenario of the MEMS arena today and the problem, where the problem is when it comes to testing, how SPEA addressed the solution for that problem. And then toward the end of the presentation, I'll give you 3 examples where we're going to go through some case studies on a real application for MEMS product. So, we know that since the year 2000, the market of MEMS have been growing ever since. And for some particular product, for some particular MEMS product, the erosion of cost in selling price has been quite important. So there is one side of the equation on how to keep margin high for those who produce in design MEMS, which has to do with some key factor. One of them is how to keep the yield in production high. This has been a challenge for pretty much every IDM in the MEMS arena to try to keep the yield of their production up. The second part of the equation is the one that involves not only the IDM, but also companies like us, and has to do with the standardization for manufacturing and especially test. We come into the equation on the testing side. And we have seen also another aspect, which is the outsourcing of the testing solution. Outsourcing because, especially in the last 10 or so years, has become very evident that keeping the test capability in-house for IDM has become very costly and inefficient. The other challenge that we have on the testing for MEMS product is that MEMS, there is a wide variety of MEMS devices. Those are require typically application-dependent solutions for testing, which of course adds to the mix and the complexity of the problem. This creates inefficiency, especially on the cost side, and the scalability of this solution as we look forward for mass production, as we pass the stage of engineering and design, and we look forward for mass production. This becomes a huge problem that needs to be solved if we want to keep the cost of the testing down. So how did SPEA approach the problem? Well, we approached it with what we call the test cell. And in particular here, I'm going to talk about the test cell value. The test cell is a composition of different elements. The first one is the tester. The tester is the unit that is used to provide electrical stimulation for the MEMS. Whether it is a pressure sensor, inertial sensor, it doesn't matter. You need some electrical stimulation for the interface. And we design a tester that can be used for any type of MEMS that there is on the market. So that's why we call this solution standard. So never has to change. The second portion of the test cell is the pick and place. If you think passing the stage of engineering and you're starting to approach mass production, you need a way to test multiple devices in parallel at the same time. So you need an equipment that is capable to move a lot of components at the same time and testing them in parallel at the same time. We designed the pick and place handler, which is the one that you see on the bottom. This is another standard unit that we designed and can be used for any kind of MEMS testing that we have that we can face today on the market. So also this portion we call 100% standard. The third portion is the hot and cold generator. Many of these MEMS are used in the automotive industry, for example, or in the aerospace, and they require to be tested over temperature. So we have a hot cold generator that we design that can be used for any MEMS application. There are two things that are not standard and are basically application development. The first one of them is the stimuli. So the one that you see on the top, depending on if you have a pressure sensor to be tested, an inertial sensor, a magnetic sensor, depending on the nature of the sensor, this unit has to be application dependent. And then the second one are the sockets, obviously, because the packaging with which these MEMS come is very different, and each one of them requires its own application, its own sockets. So with the exception of the two units that I show you on the top, everything else is a standard. And why that matters? Well, if we look on this slide, you can see the range of different stimuli that SPEA can offer for testing MEMS. For example, in the inertial arena, the first one that is represented on the slide is the low G accelerometer. So we have a table, the unit is called the rate table, and the rate table is capable to test low G accelerometer, gyroscope, high G sensor, and the 6 degrees of freedom sensor. This is a work that for SPEA began 20 years ago, working with our friends in ST Micro in Italy. And then from there, we have added other stimuli. For example, we have environmental stimuli, barometric sensor, humidity, temperature. The same unit can also be used for testing gas sensors, CO2, and so on. We have pressure sensor stimuli. So if there are MEMS that require a pressure sensor MEMS that require test, we can perform absolute test or differential test on pressure sensor. We have done tests on TPMS, force sensor, and so on. And the list continue on the light sensor, on the magnetic sensor, and on the acoustic, as you can see over there. So the design that we chose for this kind of stimuli is such that the integration in our equipment becomes very simple. So, for example, if we think about the first stage of MEMS development, where you don't have a huge amount of volume to be tested, but you have the need to test the components, all you need out of the test cell that I described before is the tester, is the thermal conditioning unit, if you need to test over temperature, that is. And then, of course, you need the stimuli. Now, the stimuli that I'm showing over here is exactly the same stimuli that tomorrow will fit into the pick-and-place handler, hence the scalability. So for engineering solution, with a simple investment, a small investment, you can address the testing need for this kind of sensor. Then when the phase 2 comes, so when your volume starts to pick up and you have the need to test more and more components, not quite yet at the volume of scale, but enough that requires some sort of automation. As you can see, you can wrap around the stimuli that we had before. You can wrap around the pick and place handler, and you can introduce also the testing sockets. So now, instead of testing manually a few units at a time, 1, 2, 7, now you have the ability to test 49 of them at a time. So meaning that the pick and place can pick 49 components at a time from the tray, move them into the sockets, test them all together, and then sort them out as they come out. So now the volume starts to pick up. But let's just say that this is not enough and your volume increase even more. That's when the third step comes. So in this particular case, what you see represented here is an example of pressure sensor stimuli. And in the previous slide, you have seen that there was only one pressure chamber in the stimuli, but the stimuli can be equipped with 3 pressure chamber. And so, for example, if you have to perform test on a pressure sensor on different temperature at different pressure point, you can set each one of the three chambers at different temperature. And so the device can move from chamber number 1 to chamber number 2 to chamber number 3, be tested at different temperature at different pressure point. And so the characterization curve of the device can be extracted, and then you can calibrate your sensor before you ship to your customer. Now, in this case, you have 2 or 3 testing chamber. The number of sites increase. It can be 49 by 1, or can be 49 by 2, or 49 by 3, depending on the number of chambers that you have. So that's the concept of the scalability of the machine. The third portion of the equation has to do with the OSAT. So as you can see, there are some of the OSATs that are already using the SPEA equipment, and some of the IDM that I see in this room are also adopting our machine. We are not the only one testing MEMS on the market, but as you can see from the chart on the right, given the long history that we have in the quality of our product, taking the top 20 company in terms of revenue, 56% of them test on the SPEA product. So I want to give you briefly 3 case studies, one for inertial sensor, one on the pressure sensor, and one on the magnetic sensor. Those are some insights on how the stimuli works, more than the pick and place or everything else. So I want to point out the picture on the bottom left side, where you can see that there are 2 units. Each one of them is called the rate table. Those units are used to test inertial sensor, whether they are accelerometer or gyroscope. And the reason why we have 2, again, is to push productivity, because we want the number of these components being tested to be as high as possible. With the 2 rate table, we can reach a parallelism of 140 devices in parallel. So we can test 140 of the sensor in parallel. We can use the double rate table in a single handler, so 2 of them can fit inside the handler. And the same setup is suitable for gyro and accelerometer. On the chart on the right, the reason why we want to show this chart is because we want to show the differences between the ideal behavior on positioning, for example, for the 2 motors that are present in the rate table, comparing to the real oscillation that you get during the breaking point. By the way, what is called here on the top twist and tilt are the 2 motors in the rate table. So if you imagine to have the rate table being like a table, the tilt motor is the motor that does this motion, and the twist is the motor that does the other motion. So the combination of the 2 allows to test the accelerometer and the gyro on all the 6 axes, all the 3 axes, excuse me. So you can see that the precision and the accuracy of this motor is very high, and 0.01 degree position accuracy on the accelerometer, and you will see 0.1 degrees per second is the accuracy on the gyro. So how do you test an accelerometer? Well, for those of you who don't know, the accelerometer has 3 axes, and so you can see here all the 6 combinations that you need to test to apply positive 1G and negative 1G on each one of the 3 axes of an inertial sensor. So the combination of the position of the components with respect to the gravity of the earth determines the axis that you are exciting at every moment. Whereas for the gyroscope, there are 2 ways of testing it. One is providing a sinusoidal speed profile that you see on the bottom, or the other one is providing a constant speed profile. And we are able to provide the sinusoidal speed profile or the constant speed profile on each one of the 3 axes of the gyro as well. So in this example, you can see on the video that is playing right now, you can see the rate table applying a constant speed profile on at 200 degrees per second. Now it's vibrating, providing a sinusoidal speed profile. And the stroke, what we call here the stroke 0 to 360 degrees, this is the motion, the entire motion that the rate table has. So the point here being is that with this kind of equipment and all the different motion and the combination of motion that you have, you are capable to test pretty much any accelerometer and gyro that we have on the market. And today, as you saw before, we have 2 of this rate table in each one of the pick and place handler performing this kind of test. Here you can see another example. The picture that you see on the video that you see on the left side is a different rate table. This one is even more advanced because not only perform the motion for the inertial sensor, but embeds the tester inside the rate table. Before in the previous slide that I showed you, you saw the tester as a separate unit. In this case, the tester is inside the rate table, so is inside this object that is moving. And with this in this configuration, we can test 70 devices for each rate table in parallel at the same time. On the other side of the presentation, you can see the same pick and place handler with 2 rate table embedded in it. And here you can see an example where the two array tables are moving independently from one another. So you should imagine the pick and place head moving 49 devices at a time, or 70, depending on the configuration, moving this device, loading them into the array table, and then the array table automatically starts and perform this test over temperature, by the way. This the temperature span can go from minus 55 to 200 degrees. Okay. Moving on. The second case study. Okay, the second case study has to do with the pressure sensor. Here you can see the number of sites tested in parallel is 392 sites. We have 3 independent pressure chambers. And in this cartoon that you see over here, you can see that the pressure is applied on the bottom side of the chamber, at the top side of the chamber, controlled. And so in that way, we can perform differential test, differential test on a differential pressure sensor. Last case study that I want to show is the magnetic test. So we have devised a way to generate magnetic field for a magnetic sensor on a board, on a socket board. And the way we do that is forcing current through loops that are designed on the magnetic board. And the current flowing into this loop generates fields that are perpendicular from the direction of the current. And in the area where the DUT are placed, the direction of the field is parallel. Even though they are, the field is circular, but in the area where the device are is quasi flat, so quasi parallel. And we are able to stimulate in this way X and Y axis, as you see here. And through a coreless loop that is designed on the board, we are also able to stimulate the Z-axis. We can reach 600 Gauss of intensity of the current here on each one of the axes. And as you can see in this particular example, we have 20 devices tested in parallel with that kind of field per die. So in conclusion, we have been in the market for 20 years. The standardization is needed to reduce cost and increase the margin for those that produce and design MEMS. And SPEA obviously has a solution that answers to that question. The last slide is something about us. We have a turnover of 224 million euro for 2022. More than 11,000 systems shipped worldwide, 38 locations, and 1,000 plus customers in 65 countries. We are really a worldwide company in this moment. Thank you very much. I'll take any questions.